What's up, Accelerated Chemistry? This is Mr. Spirk, and this is your Chapter 19, Section 4 notes on neutralization reactions. So we're going to be looking at acid-base reactions. Suppose you mix a strong acid with a strong base. So we're going to add HCl plus NaOH. In general, acids and bases react to produce a salt and water. And remember that a salt is just any ionic compound. The complete reaction of a strong acid and a strong base produces a neutral solution. This is known as a neutralization reaction. A reaction between an acid and a base will go to completion when the solutions contain equal numbers of hydrogen ions and hydroxide ions. So we can find the moles needed for a neutralization. So the term neutralization is used to describe both the reaction and the point at which a neutralization reaction is complete. How many moles of sulfuric acid are required to neutralize 0.50 moles of sodium hydroxide? So this is just like our typical stoichiometric problem that we've seen in the past. We just start with what we know. And what do we know? We know that we have 0.50 moles of sodium hydroxide. And they're asking us to figure out how many moles of sulfuric acid are required to neutralize that amount. So we just use our mole-to-mole ratio. 2 moles of NaOH is equal to 1 mole of H2SO4. And I just pulled that straight from our equation. Moles of NaOH cancels out, and we are left with just moles of H2SO4. We do the math, and we get 0.25 moles of H2SO4. So 0.25 moles of H2SO4 will neutralize 0.5 moles of NaOH. So now we're going to start to talk about a type of reaction and something we can do in the lab called a titration. You can use a neutralization reaction to determine the concentration of an acid or base. The process of adding a measured amount of a solution of known concentration to a solution of unknown concentration is called a titration. The steps in an acid-base titration are as follows. The first step, a measured volume of acid solution of unknown concentration is added to a flask. Several drops of an indicator are added to the solution while the flask is gently swirled. Measured volumes of base of known concentrations are mixed into the acid until the indicator just barely changes color. It sounds like something so simple, but these are actually very hard to perfect and very hard to get just right. But this is what it looks like in the lab. Let's start on the left and work our way towards the right. A flask with a known volume of acid and an indicator is placed beneath a burette that is filled with a base of a known concentration. In the center, the base is slowly added from the burette to the acid, and then a change in the color of the solution is the signal that neutralization has occurred. The solution of known concentration is the standard solution. Neutralization occurs when the number of moles of hydrogen ions is equal to the number of moles of hydroxide ions. The point at which neutralization occurs is called the equivalence point. The indicator that is chosen for a titration must change color at or near the pH of the equivalence point. The point at which the indicator changes color is the endpoint of the titration. So this is what the pH curve looks like for a titration. This graph shows how the pH of a solution changes during the titration of a strong acid with a strong base. The initial acid solution has a low pH of about 1. As NaOH is added, the pH increases because some of the acid is reacting with the base. The equivalence point for this reaction occurs at a pH of 7. As the titration nears the equivalence point, the pH rises dramatically because hydrogen ions are being used up. Extending the titration beyond the point of neutralization produces a further increase of the pH. If the titration of HCl and NaOH could be stopped right at the equivalence point, the solution in the beaker would consist of only H2O and NaCl, plus a small amount of the indicator. And that's because at the equivalence point, we are neutral. We have no acid or base present. So we can determine the concentration by a titration, and that's the whole point. So if we have a 25 ml solution of H2SO4 is neutralized by 18 mils of 1.0 molar NaOH, what is the concentration of H2SO4 solution? So again, we just kind of start with what we know and we use some stoich to figure this out. So for this, we know the volume of NaOH we use. So we start with that. So we start with 0.018 liters. And we have to use liters because we're multiplying by the molarity. And the molarity is 1.0 moles of NaOH per liter. So now that we're at moles of NaOH, we can use our balanced equation to go to moles of H2SO4. So we have 2 moles of NaOH for every 1 mole of H2SO4. So remember, they're asking us for what is the concentration of H2SO4. And concentration, or molarity, is mole per liter. So we have moles of H2SO4 on top. Everything else is canceled. So now we just want to divide by how much H2SO4 we have. And we have 25 milliliters, or 0.025 liters. So that gives us a unit of moles per liter. So we multiply that through, we get 0.25 molar H2SO4. So we had a known volume of H2SO4, but we didn't know what concentration it was. So by using a known volume of a known concentration of NaOH, we can determine the concentration of that H2SO4. So in review, in general, acids and bases react to produce a salt and water. Neutralization occurs when the number of moles of hydrogen ions is equal to the number of moles of hydroxide ions. And that's it for section 4. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry, 2012 edition of the textbook, the resources CD, and pearsonchem.com. Have a great rest of your day.